Hi everybody. Today's lecture is on solving problems and debugging. So with these shell scripts that we've been learning, how you debug these things might be a bit new for you. They're not like traditional programs. They're not like traditional compiled programs. So figuring out how to actually understand what's going on can be difficult. So in this lecture we'll talk about that, and we'll talk about these things in the context of Program 1 and how we can get closer to getting that done. So our challenge for Program 1 is that you've been asked to write some software, you've got specifications for it, but maybe you don't understand the underlying technology. Maybe you don't even understand all the specifications, and maybe you're not sure how the different components actually work together. So the advice we're going to talk about here is going to apply to every single software project that you encounter in life. And it probably applies to a lot more too in your life. You can apply this at other cases. But the trick is to divide and conquer. We want to break the problem into smaller and smaller pieces, and then ask ourselves about each one of these pieces. Do I already know how to do this? If not, does it seem easy? Does it seem like something I can learn how to do? And if not, we can break it apart further. So for Program 1, our core task, let's identify what that is. It's to compute statistics. Now let's ignore the rest for a moment, handling signals and the other things. The core task, let's break that down. So the statistics that we're supposed to compute are do the statistics on rows and on columns. And let's just do one of those. How do we compute the stats for just rows of data? We're still not sure how to do that, so let's break it down even further. How do we compute the statistics for just one row? Forget about all the other rows. How do we do it for just one row? Now, computing statistics for one row can be broken down into we need to read a line from a file, and we have to figure out how to sum the numbers on that line. We need to know how to divide by the number of numbers on that line, and we need to be able to print out the result. Now, those look doable. Those are things that we can actually start to work on. So let's look at the first one here. How do we read a line from a file? Well, as we learned about in our last lecture, we started to learn about the read command. So this time, as you start reading through the sources that are available to you, as you start doing Google searches, as we start asking your friends, the question, how do I read a line from a file in Bash, is a much, much simpler thing than how do I calculate statistics from a file. So as you read this technical documentation, this is where man pages really come into their own. These reference manuals have descriptions of the different options that are available for these commands. You're going to pay closer attention to what you're reading. You'll remember it more. Now that you've got a goal, your brain is focused in on finding the pieces of that small little puzzle that you're working on. So we come across the read command, as we talked about, and what read does is it primarily is used to get data from standard in. You can use it to get data from a file. You'd use the -u option for that, but typically it's just used for getting data from standard in. So let's write a little sample script to see what happens. So here's a script called read test, and this one I've just plugged it full of different things that I'm trying out. So I'll start off my script with my shebang, and then I'll tell the user what to do. Enter in a string and then hit enter. Then I use the read command, and I read into this variable, myvar. Then I output that back to the user to test what just happened. Did I actually get the data or not? Let's test and see what that was. So enter back out myvar. Then let's try dumping it into a file. I'm going to echo that myvar out and put it into a file at file name, temp file name, process ID. Then I'll put it in 2 more times just for grins, and I'll append that twice more. Then we will echo out to the user that the temp file contents are the following, and we'll play around with getting data from a file. So then I cat it out, which should be the contents of that file. Next, let's try to get the first line of that file, since that's what we're testing here. The first line of the file is, and then here's how I'm going to do it. I'm going to use the read command again, and then here's my variable. So I'm going to read into this variable called entire line, and we know that that is going to return just the first line. Now read is looking for data coming in from standard in, so I can't just give it a file name to read from. So how do I get data from a file in as to be input as standard in into something? That's exactly what this operator is supposed to do. This is the standard in redirection operator, and it opens up a file, takes the contents of it, and stuffs it in as standard in to make it available for read to read from. Once that's done, I will echo it out, and hopefully that's the first line of our file. Now let's play around with some of the variables in read. So here I've got read and then first word and rest of line as a second argument. And again, getting data for this, I'll get it from our temp file. So when I echo this out, I'll indicate to the user that the first word of the first line was the first word variable, and that the rest of the line was the rest of the line variable. And then I'll clean up my temp file. Now, if we look at the actual output for this thing, which I've been building up as I've been testing out this program, all the stuff at the beginning makes sense. We've seen that before. Here's the 3 copies of the file we entered into there. And our read entire line worked. It grabbed just one line off the file. This sentence is false. Here's that line. Read entire line, get the input from temp file name. And again, that returns just one line. The last 2 lines here indicate that the first word of the first line was this, and that the rest of the line was sentence is false. And from that, we can see that when you use the read command with more than one option, the first word is going to be stuffed into the first argument that you use in read, and then anything else gets stuffed into a rest of variable. So this works really well if you're able to write your script in such a way that we know exactly how many variables are on that line. But how often does that happen? So we figured out how to read a single line from standard in into a variable. And over here we've got our little test script that's looking at it. Here's our read test script, and we've got the shebang line up in the front, and we can see how we've got our read single line var, which is going to take its input and from standard in and put it into a variable, and then we echo that variable back out. And then when we set up a data file called data, so we cat it out and we see it's just a bunch of numbers. And then when I cat this file and pipe it into readTest retrieves that from standard in, which it got because of the read command, and the standard in was given to it by the pipe, which got its data from cat data. So this output line, we have written a program that is able to grab data from standard in and display it on the screen. So this is something we knew, how to read a single line from standard in into a variable. For testing our knowledge, the tiny shell script here is a critical thing. Your space, your web space, your server that you're logging into should be filled with little tiny test scripts like this that you are using to experiment with the different commands that are involved in writing program 1. So now let's try summing up the numbers on a line. So to decompose that a little further, how do we add 2 numbers? And then we'll worry about actually getting those from a line. Well, we remember from previous lectures and from the documents that we can add 2 numbers and store them in a variable with the expression command, and that specifically we have to use a subshell to do that calculation and resolve it before we can stuff it into the variable. We can even use variable names and grab them from external variables as opposed to just entering data directly. So how do we take those numbers from the line that we've read? And as an additional challenge, what if we don't know how many numbers are actually on the line? So we know that read and then some variable name is going to read the entire line into one variable, but how do we break that up? So the documentation might not be as useful for this. So putting it up on a discussion board for help, asking your friend, looking online is probably going to be a better case for questions like this. We remember that we have done this kind of thing already in our for loop. So we've looked at for loops as a way to parse data from a line of variable length or from indeterminate length. So again, we've got a data file that we can cat out and verify the contents of. Now we have our script called read loop test. Now in this script, we are reading in from we're reading from standard in into a variable called myline, and that's going to take the entire line and stuff it into one variable. Set a summing variable equal to 0, and then start a for loop up. And this for loop is going to run as long as myline, the variable that we read into, has separate distinct values separated by white space in it. So we don't know how many is in this for loop, but it's going to keep running until it finally runs out of entries in that variable. For each one of those, we're going to take our sum variable and add it to whatever we just read from the variable. So this is going to sum up all the numbers on that line, and at the end we echo it out. When we try to use this thing, we would cat our data file and pass it in as standard in to read loop test. Remember that our read loop test isn't designed to read data directly from a file, it's designed to read it from standard in because of our read myline construction here. So the way we call it has to be where the data comes in via standard in. And when I try this, Bash reminds me, hey, you don't have permission to run this. This isn't really a program. What are you trying to do? And the way we fix that is with changing the mode and adding the execute bit to this particular file. This is the classic standard way to add execute permissions for something you want to be an executable. We don't actually touch more on the change mode functionality until we hit block 2. Well, we'll look at it from the perspective of Unix files, but for our purposes here, this is the line that's needed when Bash says, hey, permissions denied, you can't run that. Alright, so once we've set up the permissions, then we run our script, catting data into read loop test, and it sums it up. 6 plus 4 is 10, plus 4 is 14, plus 7 is 21, plus 7 is 28. Whew! And my mental math even worked out and got the same value as down here. Okay, so printing this thing out. So dividing by the number of numbers on the line, and figuring out how to get that out. We're going to decompose it a little further. How can we tell how many numbers are on the line? So sure, we can sum it all up, but we need to know how many numbers there are there so that we can divide it by that many to get a mean. So, well, how do we divide two numbers in the first place? Well, with our script here, we know that we can simply add a count variable to what we had, and then use the division operator instead of addition. And then to print it out, we'll use printf. So additions to our code that we had on the previous slide, we've added a new count variable starting at 0, and every time through our loop, simply increment the count variable by 1. So yes, let sum keep summing up all of the values of the variables, and use our count variable here to add 1 each time we process a number. And at the end, calculate a mean by doing the sum divided by the count. That is a simple mean average. Now, what we get out of this thing at the end is an integer value. And that happens because the division operator here with expression, it only works with integers, so it doesn't do floating point math. To figure out how to do floating point math is something that we're going to leave up to you to figure out. There's several ways to do it. Certainly you can ask questions on the discussion board about it, but figuring out how to get the correct value out of this and then round appropriately is part of the puzzle here. Okay, so to summarize, we've broken down this problem until we have a tiny problem that we could actually do. And then we used documents and friends and discussion boards and searches to figure out the solution. And you're going to learn a lot more if you're reading with a well-defined problem. Solve that tiny problem. Make sure you actually spend the time to solve that problem. Write that code, make the little sample script, and feel good about it. You know, have a donut. My problem is that I have donuts before I have solved the problem. I just eat donuts. But certainly rewarding yourself for that is a fine thing. Now work upwards. Integrate what you've just done into a slightly larger problem. So take what you've learned from that sample script and integrate that into your primary program that you're writing. And then repeat. Just keep doing that until the problem is entirely solved. We have a shell script compendium online as one of the articles, and it has an example script in it called big loops. And big loops is going to read all of the lines from a file, add them up, and then compute the averages. So you can go see how that works right now on this big loops program that I've written there for you. And it'll help you with getting program 1 up and running. Okay, now we are going to take a look at debugging. So debugging is the art of figuring out why something went really wrong. So testing is done to find the bugs, and then debugging is what actually removes them. So the first part of our process for debugging is that we have to have a problem that's reproducible. If it's not reproducible, it's extremely difficult to find the problem. This is something that happens more in C, where we have memory that is variable and changing every time we run the program. Or if we're using, uninitialized buffers and uninitialized dynamic memory, we can get ourselves into some truly strange intermittent problems. It's not as big a deal with shell scripts, but still something to be aware of. You got to be able to reproduce the problem. So often that means simplifying our input and simplifying the environment until the problem can be replicated whenever we want it to. So one way to do that is with the wolf fence algorithm that we'll talk about next. Some of the challenges that make it hard to reproduce this problem is that there could be a unique environment. So maybe you're up on the space station, or maybe it's your Aunt Edna's PC and she lives in New Jersey and you don't. There might be a particular sequence of events leading up to an error that are unknown. You might not know what events transpired to make that occur. They might be difficult to do more than once. There might have been a lightning strike, or maybe it turns out that Aunt Edna is trying to watch Netflix through her toaster, and it's not actually her PC that's the problem. I remember when I was running my IT company that one of my employees described a job that he went out to solve where he had received a phone call from a lady who had a problem where every time she pushed a key on her keyboard, it beeped at her. And she didn't understand what was going on. And he was able to remote control in to her computer and could not find this problem. He would push buttons on the keyboard and there'd be no beep. So he was unable to reproduce this issue remotely. So finally he got in the car, drove out there, spent an hour getting there, and when he got there, the problem was that she had a book sitting on the control key of her keyboard. And she hadn't noticed that, and there wasn't something that my employee knew to ask. And so that problem was so unlikely as to be something that's difficult to reproduce, and that sequence of events was so unlikely that often getting there and examining it by with your own two eyeballs is the only way to solve it. And sometimes you can't. Sometimes it's a strange sequence of events that got you there. So once you can reproduce the problem, we're going to try to examine the state of the process at the time of the error so that we can see why it crashed and died and then fix it. And we're going to look at three different types of examining the process state. First of all, live examination of what's going on, post-mortem debugging, so after the failure debugging, and then trace statements. So the wolf fence algorithm is a fancy, complicated way of saying start commenting out sections of your code until the problem disappears, or you've reduced the input space down to where you can focus on what the actual problem is. So if you can't find the source of the problem at all, you don't know where this is coming from, or you can't reproduce it, you narrow it down, you divide and conquer. So bifurcate, which is a fancy word for split, so split it in two by commenting out half of your code and then running it again. Maybe change it to ignore the way the input is coming in entirely. So is it the input that you're getting is bad, or is it just your code? Well, if you start commenting pieces of your code out, eventually you'll get down to a simple thing that you know works, and then you add them in line by line, one by one, until it breaks again, and then whatever just caused it to break, that's the problem. So the wolf fence algorithm is this, and this came from one of the ACM papers back in '82. There's a wolf in Alaska. How do you find it? You build a fence down the entire state, and then you wait for the wolf to howl, and you determine which side of the fence it's on. So then you go over to that side of the fence, and you build a fence down that half of what's left, and then you wait for the wolf to howl. And you keep doing that until you get to the point where you can see the wolf. Same principle. Comment out chunks of your code, simplify it until you can understand what's happening, and then gradually put it back together. So live examination is something that's hard to do with shell scripts. You can do that wolf fence algorithm where you're commenting out code with shell scripts pretty easily, but live examination is really difficult, if not impossible, to do on shell scripts. Typically, there's going to be some separate application that allows you to pause the process execution and look at the contents of the variables in the stack directly. So if you've used them before, common integrated development environments like Visual Studio or Eclipse or MonoDevelop, which is used in the Unity framework for you game developers out there, those allow you to examine the running code directly and see what's there. You can look at the variable values as it runs. You can see the stack, the function traces that the functions that it has called to get itself to that point. You can even reach in and change around the order of execution. You can change the variable values. Pretty crazy stuff. These debug applications can even be connected to processes that are on other machines, so it's called remote debugging. But I don't know how to do this with shell scripts. I don't know if it's possible. On the same token, post-mortem debugging is also difficult. So after this program crashes, Unix leaves behind a core dump file that can be examined. This is just part of the Unix operating system. So that core file stores the contents of a host of different stuff. So all the virtual memory contents that that process was using, all the contents of the CPU registers and the program counters and the pointers and everything else that that program was using, all of that gets dumped into a file, except with shell scripts. You don't get anything like this to examine. So the only thing you'll get out of the shell script is whatever errors occurred that were displayed on the screen before the script stopped running. If you had one of these core dump files, you could use the GDB program to open it up and take a look at it, but we don't have one of those. So we'll look at GDB again in some detail when we hit block 2. Trace statements is going to be your bread and butter, and this is going to be my first comment every time you have a problem. So every time you want to ask a question like, I don't understand why this is outputting what it is, or I don't know where this queue is coming from, I don't know where this new line is coming from. The answer to that is trace statements. And trace statements have two categories. So one that is printing out the value of the variables as you go. That's the what of it. The other one is printing out where you currently are. That's the where of it. So what and where. So imagine we have a loop. So our trace statement here is saying, I am about to begin a loop and the value of variable j is 0. This is obviously diagnostic information that you wouldn't want the user to see when they were running the script, but as we as a debugger are going, we know that there's a problem with one of these variables, we just don't know what it is, so we tell ourselves where I am in the program and what the value of the variable is so that I can see it as it runs, and I make sure that I output this to the screen or to a file so that I can examine it after the fact. Maybe my next line says something like, okay, now I'm at the start of a loop. I've just begun the loop, and I now have a new looping variable I. So let's go ahead and start using looking at the value of that variable too. Now I'll run the sum function, and my sum function updates I appropriately, but j gets just garbage. It's filled with gibberish. So something is wrong with my sum function. Now, was it inside the sum function? That might call for additional trace statements inside sum. What lines of code were between the trace statement that says now at start of loop and sum function ran? Was there additional lines of code in there that you need to add more trace statements to? Probably, because here we have that the sum function has already ran and j is toast. So if this thing keeps running, the garbage in, garbage out principle continues to hold. So maybe we execute a file read and j is really getting ugly. We're starting to get some strange characters, some non-printable characters that are occurring here. Maybe when we actually follow through and execute that file read, the contents of the file that it succeeded at, either it failed or it never got data in the first place. We don't know. But remember, it's a shell script, right? So it keeps running, even if there were horrible errors, and you just watch this unfold as the whole thing goes. And things even get bad. I mean, at the end of the loop, by the time these shell scripts are done running, your trace statements are filled with a real horror story. So debugging our shell scripts. Well, let's take a look at some tools that we can use to do that, that can augment our trace statements. One thing you can do is you can enable printing out of command traces before executing each command. So we can add the -x switch to the end of the first line of the script. So in our shebang line here, we can add -x. Another way to do it is you can start the script up by saying bash -x and then the name of your script. And what that does is it enables these command traces. And what do those look like? They look like this. So what we have here is the original sum loop that we have seen before. And our sum loop just prints out the value as it increases from 8 to 15 to 21 by summing up 8, 7, and 6. But when we have the -x switch involved with bash, we get output for each one of the lines executed in the process of doing the loop. And we can even tell when things are nested down into a subshell with this double plus instead of expression, and single pluses for other lines that it's giving us. And these single pluses, any line that starts with a plus is something that's being output as one of these command trace lines by bash for us. So this can be kind of handy. I find that this is too much. I find that I like to be able to display the trace statements that I want to see, and not necessarily all the commands that bash is going to output. Maybe this works for small scripts, maybe not. You can certainly use it as another tool in your bag of tricks. And as a final thought here, I wanted to talk about something that's commonly done that doesn't work. So this is kind of a complicated script. When I run this thing, note that I didn't cat it out in the beginning. When I just run this thing, what it does is it immediately says the contents of the read pipe test file are, and then it displays itself. So if you look into this thing, it basically it prints itself out in the beginning. That's what it does. But the real thing I want to talk about is this line. Here I have cat read pipe test. So that grabs the script itself, loads it from disk, and then sends it to standard out. So then we intercept standard out with this pipe and redirect that to the standard in of the read command. So read grabs standard in as it comes in, and it takes that data, extracts the first line, and stuffs it into first line. And then the process goes on, and then it outputs the value of first line. This seems like there isn't a problem. But the issue is that if you actually look at the results of what first line is, first line has no contents. For some reason, this didn't work. And the answer is because of subshells. What's actually happening here is that inside, there's a separate subshell that is generated by this pipe operator. So yes, data was stuffed into it from the standard out of the cat command, but the pipe operator that took the data in as standard in created a whole brand new shell. And in this shell, the data is read into the variable called first line, and then this particular subshell is destroyed, and the value of that variable is lost. And first line as a variable is out of scope compared to the rest of the script that was running. So this script doesn't have any idea what the variable first line is. That was part of some subshell that it has no concept of, so the value is empty. Anyway, the upshot here is that you cannot pipe to read. So if you find yourself doing this, this is the reason. It'll never have data, and I just want to give you a heads up on it. Well, I hope this lecture has been interesting for you. We've got some ideas about debugging techniques. Please, please, please remember to sprinkle trace statements all over your code. They will solve your problems for you. They will show you where the problem is, and it'll just leap out at you. Oh, that's the problem. How could I have done that? So please remember to add those in there. If you have any questions, feel free to post them on our discussion boards, and including your programming questions. We can't wait to take a look at them. Thanks.